Hey everyone, this video is introducing the term systems and then just a basic strategy of how we're going to start applying Newton's second law to systems. There's going to be another video, D.8, which is an example problem with me working through a specific type of question all about systems. So here we go. To start off, our simple introduction to systems. The basic definition. Really, at the most simple level, a system is just referring to the objects that you're considering in a problem or in a given scenario. If you have 5 objects, you might have a system of all 5. Or there might be a time when you're just going to look at one object, maybe calculate that one object's velocity. Then your system would just be that one object. Our systems in this class have really always just been single things, whether it was a box or a car on a ramp or something moving at a constant velocity, whatever. Up until now, we've always been considering one object at a time. Well, what we're going to see is that we can use our knowledge of systems and Newton's second law to look at multiple objects in a problem, if things are connected together, or if things are otherwise going to affect one another as they're moving. Okay? A couple things that are really important to consider when you're dealing with objects in a system, and more specifically, when objects are connected. All right? When objects are connected, they're moving together. So that means 2 things. One, they're going to have the same acceleration. If they're both moving together, whether they're connected by glue or by string, all right, whether they're just being pushed against one another across a flat surface, they're both going to be moving together, so they must have the same acceleration. Okay? The second thing is really due to Newton's third law. When there are 2 objects, or more, but let's just stick with 2 right now. If there are 2 objects pushing each other, they must be pushing on one another with equal and opposite forces. Whatever forces are acting from one to the other must be equal to that force that the other is applying back on that first one. Just third law. All right? Our strategies specifically then for applying Newton's second law, they are very similar to our other strategies. They're always hinged around understanding your coordinate system, your free body diagrams, breaking things into components, and then setting up Newton's second law as needed. The first thing, you don't necessarily have to write anything down for number 1 for a problem. Just know, oh, there are 2 objects I need to worry about, or there are 3 objects, or all of our problems before now have just been 1 object. So know what things are happening in a certain scenario. Next one, draw your coordinates. All right, we've seen this story. Okay, you should know which direction is your positive and negative. I will say for this one, there'll be some problems where you could draw 2 different coordinates, one for one of the objects and another for the other object. I'm going to put a star here and say that the direction the objects are moving, it's nice to make that the positive direction. So let's say object's motion is positive. If you follow that, it's going to keep you nice and organized, and you're not going to get tripped up when you have positives and you're supposed to have negatives. Okay, but that's for a certain problem. The example problem will show that. Okay. Next, draw free body diagrams. You've done that before. Now you're going to do it for each one individually. If there are 2 objects in your system, draw a free body diagram for both. For 4, if you have things acting at weird angles or if things are on inclines, you should break it into components. And 5, we should be setting up Newton's second law. We apply the sum of the forces in the x direction, the sum of the forces in the y direction. You add up those forces, you set it equal to ma. Add up the forces, set it equal to ma. Sometimes things will be in equilibrium or at rest, and this is going to equal 0. Sometimes it won't. Sometimes we might have tilted axes, sometimes we won't. But yeah, apply the second law. The last thing is really just a real quick sample scenario. It's not even going to be a fully worked out problem. Okay, but let's say here's our scenario. Mr. Thrasher is pushing on 2 boxes, and I have those boxes on wheels just so we can ignore the friction. the big blue box has a mass of big M, and the little green box has a mass of little m. And I'm pushing this big box with a force that I'm calling F big M, the force on the big box. Okay, let's set up the second law. Let's just go through our general strategy. I have two objects in my system. Step one, done. Easy as that. All right, for step two, if I go back, if I have to remind myself, draw a positive and negative coordinate system. Let's just say going to the right is positive. They're both going that same way. All right, and I'll say up is positive. That's what I normally do. I don't have to break down anything into components here, but let's draw free body diagrams, and you gotta be organized. I have two objects. I'm gonna actually write out in my chicken scratch handwriting, object M, big M. And over here I might write object little m. Because now not only do I have the sum of the forces in x and y, I have multiple objects. So for big M, you only care about forces acting on that object. So there's of course a normal force, Fn. All right, and if you want, you might want to put in, oh my gosh, an M for the big box M. There's a weight, Fw M. And here's my pushing force. That's from this one right here in orange, Fm. Uppercase M. That's it, no other forces. There's no friction. So this is the free body diagram for this blue box. For the other object, if I actually switch to green, that would make more sense. Well, there's a normal force on that little box. I could call that Fn for the little m. There's a weight, Fw little m. And, well, this blue box here is pushing on this green box. So there must be some kind of contact force. I might call that F big M onto little m. Aha! This actually means my free body diagram over here is incomplete. So I lied to you when I said I was done. If the blue box is pushing on the green box, by the third law, that green box must be pushing back on the blue one with an equal and opposite force. There's my completed free body diagram. What's in red is kind of the normal stuff we've seen. Okay, what's in green here is fairly normal. You recognize that the blue box is pushing on it. But then, oh my gosh, I have to go back. Because if the blue is pushing on the green is pushing back. Okay, and just so you know, this force M here is not, or at least it does not have to equal this force. These two do not have to be the same. These are not examples of the third law. Okay, they're both acting on the same object. That can't be true. Well, what I could do then for box big M, I could write out the sum of the forces in the y direction. And I could say that Fnm minus Fwm equals ma, which equals 0. Sum of the forces in the x direction. I could say Fm big M minus this one right here, Fm little m equals ma. Oops, in fact, I should even, if I undo that, I should even make sure that's a big M times a, because this is big M. I don't actually know, it didn't say in the problem if it's moving at a constant speed or not. But notice, everything here I did for this box, free body diagram, and the sum of the forces. I would repeat again over here, the sum of the forces for box little m in the y direction. That would be Fnm minus Fw little m. You see me running out of room. Same thing. So I'm just doing everything I've been doing before, but just I have to do it for both objects in my system. Okay, here it's just this one force. something like that. All right. Next video is an example problem.